Welcome back to lecture 11.2, where we're going to begin our explorations beyond the ideal gas, right? And in particular, we're going to do what's something called the hard sphere gas today. Okay, so just a reminder, we did our demonstration last time. We worked out this process of throttling, also called Joule-Thomson or Joule-Kelvin expansion. And we showed that throttling is isenthalpic. So this is still true, but for an ideal gas, isenthalpic process is also isothermal. And remember, instead, when we did our experiment, when we had a change in pressure of about 2,000 psi, or about 136 atmospheres, what we ended up with was for helium a temperature change of about 6 degrees positive, and nitrogen a temperature change of minus 22 degrees negative. Okay, so how do we understand these values that we didn't expect? Okay, well, the first thing is throttling is isenthalpic. There's nothing wrong with that process we did, but we see that this isenthalpic process is also isothermal for an ideal gas. So we're going to have to go beyond the ideal gas. And the first question we ask ourselves is, what is ideal about an ideal gas? What are we neglecting when we say it's ideal? So what is it that we're ignoring? So the key is that we're actually ignoring any interatomic or intermolecular forces. Not inter, right? So now we have to actually say, well, what would be the interatomic forces? So imagine I have two atoms, right? Separated by a distance we're going to call r. In fact, this is not, these things are not ideal where they neglect each other entirely. There's this entire field that's called chemistry, which is basically has to do with these interatomic forces. Right? There is polarizability, and there's all these things. So there's actually what we'll call a potential landscape. That is, there's some potential between them, which we're going to call phi. And this is typically described in what's called the Leonard-Jones potential. The Leonard-Jones potential. Maybe you've seen the Leonard-Jones potential before. Looks something like this. So there's some tail as r goes to infinity. There's some minimum in this curve, right? And here, because the force goes like minus the potential over the distance, right? This is definition of force. This part is repulsive, wants to push the atoms away from each other, and this part is attractive, right? Wants to pull them. Everything wants to have this minimum in the potential. So that's quite complicated. We're not going to do the full Lorentz potential right now. We are going to instead approximate this as what we're going to call a hard sphere gas. So basically, we're going to say that each one of these atoms is a sphere of radius d. Okay? So there's some size d, and inside that radius, these things are hard, and you can't get any closer to each other. Outside, we're going to neglect any interactions. So let's draw that hard sphere potential. We're going to have, oops, that's not very straight. We're going to have the potential. We're going to have some distance r0. Sorry, some distance d, which is the spacing. Inside that spacing, we're going to make the potential infinite. Right? It's hard. It's like a, it's, you know, we've talked about these things as billiard balls before. This is really the radius of the billiard ball, right? And outside, it's 0. Okay? So, let's take this potential into account and ask ourselves, how would we imagine if there's a hard sphere, how is that going to change our ideal gas law? So, really what it's going to do is it's going to say there's a certain volume now taken up by those hard spheres that cannot be taken up by the gas, right? They can't move into a certain amount of volume because it's taken up by the hard spheres of other atoms. Okay, so what that means is if we imagine that the molar volume, which is the volume per mole, is now going to go to some volume but with a correction, right? There's some volume, B, which is the gas is prohibited from moving into, because that's where. So let's calculate what that volume is. B is approximately the number of atoms in a mole, right, since this is a molar volume, times the size of those atoms, right? Which is the volume is 4/3 pi d cubed. And this is actually also approximately the molar volume of a liquid, right? If all the molecules or atoms in a liquid are sticking right next to each other, this is approximately the molar volume of a liquid. Okay, so now how is this going to, say, change any of our physics that we've had? So now we're going to say, basically, we're going to have the hard sphere equation of state. It's going to be a modification of the ideal gas law, right? So we're going to have our volume, PV, goes to V minus B. I've already divided by N here to make it a molar volume, so it's just going to have PV minus B equals RT. Okay, so now imagine, for example, I was going to do an isothermal process. Let's look at an isothermal compression, for example. So for an ideal gas, right, we went from V1 to V2 and P1 to P2, right? So what would happen if we had a hard sphere gas? So this is ideal gas. So if it's a constant temperature, I've got to go to the same volume, right? This is constant, but now this volume is smaller, right? So I have some excluded volume. So the pressure actually has to rise higher. That's not supposed to be a straight line. It's supposed to be a hard sphere isotherm. All right, the pressure is going to rise faster because the volume has an offset. Does this change U? Right? Does this change the internal energy? No, because the internal energy is still dictated by the kinetic energy. Right? And the kinetic energy didn't change. Okay, so now let's give you a few values. So we're going to have, how big is B? So the scale of B. All right, so B for helium, it's 23.7 times 10 to the minus 6. What should our units be? Well, it should be like a volume, a molar volume, right? So it should be a volume divided by a mole. SI unit for volume is meters cubed. So nitrogen, I believe, is 39.1 times 10 to the minus 6. Water would be 30.5 times 10 to the minus 6. CO2 is 42.7. And the last one I had was neon, was 17.1. If you look these up, these are really very close to their molar, the molar volumes of their liquids. Okay, so let's focus on our helium and our neon because those are the ones that I had around to do these experiments with. And by H2O, I don't mean obviously liquid, I mean water vapor. Okay, so does this explain our question? Well, let's actually stop this lecture as 11.2 and let's see if these hard sphere gases can explain our demo in lecture 11.3.